Alright, in this video, I'm going to be going through how to answer a specific kind of question in your electronics paper, which is going to be like explain questions. Right now, I've prepared three questions to go through, and they all are like explain this, explain this, explain that, explain why. So after this, you should get some sense of how to go about doing an explain question. So I have a question here. It's talking about this buggy, and basically in each like light sensor circuit, there's not really light sensor, like in each um, driver for the motor of each wheel, there's this circuit. Basically, just a bit of circuit analysis here, right? The LDR and this resistor, they combine to make a voltage divider. So the output X voltage depends on the brightness of the surrounding brightness. And then this goes directly into the base of this BJT, which is controlling a motor. So the brightness, we can translate this in our minds, right? The brightness, the surrounding brightness controls the current that is supplied to the motor, or how much the motor is being driven lah. Just basic circuit analysis. And we find that analysis actually helps us answer the next question, or the question, which is explain how the circuit switches the motor on when a light source illuminates the sensor. So you can actually already take what I said through the circuit analysis part and then try to answer this. So you can pause the video now to try and answer this on your own. Do note that this question is 4 marks. So when you see like, oh, the question is 4 marks or the question is 2 marks, you should at least have 4 points to make about the circuit and how it switches on the motor and whatnot. So yeah, pause now. Okay, so um, I'm just gonna start. Okay, wait. Before I start, right? Let me go over how I analyzed this circuit. So you notice how when I came over, right, and I immediately just started pointing out things. The way you can go about doing this is following the current. So we have 9 volts, we have 0 volts here, right? Current flows from positive to negative or to ground. So we can actually go, okay, that's really, it's quite large. Okay, so we can actually follow the current, we can draw arrows. So we can see that the current will flow this way. And then we can also note things like, oh, this is a voltage divider, right? And then we can follow this again. Then we can say, oh, okay, there's a transistor here. So if there's no current, this won't happen. So then we see, oh, wait a minute, the voltage divider is connected to the transistor. Oh my gosh, it's connected to transistor. Then you can see how these sub-circuits relate to each other in this entire circuit. So what I did was follow the current. If you notice any sub-circuits that you recognize, for example, like this voltage divider, or this like motor driver, transistor driver for a motor, then you annotate that, and then you can also say see, or you can check if those two sub-circuits connect to each other, and in this case they do. So that's like the basics of circuit analysis. And also with this circuit, right, there's a changing variable, which is the surrounding illumination. So then you would also need to see, hey, what happens if it's brighter here? Or what happens when it's darker? In this case, you need to know the graph of an LDR with like resistance against brightness. Okay, so for an LDR, right, when the when the brightness increases, the resistance actually decreases, and when the brightness is not as bright, right, the resistance is actually higher. So the graph looks something like this. And in this case, you need to know this. So this is what you need to know. Then you can see, right, when the light source illuminates the sensor, so we are looking at the brightness when it's higher. So we know that the resistance here is actually quite small. The resistance is quite small. So the next question you might ask is, okay, so what would the voltage X look like when there is not much brightness and when there is a lot of brightness? And to this, I would say that that is a very, very good question. You should give yourself a gold star, or well, Travaya can give you a gold star. So we can actually find out if the voltage, what kind of change the voltage would have by subbing in. That's weird. It's getting clipped by subbing in values for the resistance. So let's say I have two separate um, voltage dividers here. Let's say they are all being supplied by 5 volts. And then let's say this is 1 kilo ohm. And then now we're interested at this point, which is the voltage across the 1 kilo ohm resistor. And then now let's say, in this case, the resistance is 100 kilo ohms. And in this case, the resistance is 1 ohm. Alright. Using the voltage divider equation, we can actually find the voltage X, or the voltage across the 1 kilo ohm resistor. So for convenience sake, right, or to make the video faster, I'm not going to write down the equation. If you're interested about voltage dividers, you can watch the video I have on it. But I'm just going to find the voltage X. So in this in this case, the voltage at X is actually 0. In this case, the voltage is 0.0495 volts, around there. So quite a small voltage. For this case, we can actually okay, wait. Yeah, okay. I thought I did it wrong for a second, but I'm never wrong. So in this case, in this second case, sorry, the voltage is 4.9950 volts. So we can see that when the resistance for the top resistor is actually low as compared to being high, the voltage at X, or the output voltage, right, or the voltage across the bottom resistor would actually be higher. So now with this analysis done, we can say now, oh shit, I forgot 0. We can say now that when the illumination, or when there is a light source that illuminates the place here, the resistance would decrease, and as such, the output X of the voltage divider would increase. So let me write this down. Let me write this down. Okay. So first, what happens is when a light source illuminates the area, the sensor, sorry, the resistance, um, the resistance of R1 decreases. Okay. So when this happens, okay, when this happens, when this happens, the voltage of X decreases. But we may also want to add some context that R1 is actually connected with R2, which forms a voltage divider. Okay, so let's just add the context. R1 is related. R1 and R2 form a voltage divider. Okay, so as such, when R1 decreases, when the resistance, we want to be specific, we're dealing with 4 marks here, okay? When the resistance of R1 decreases, using the voltage dividers equation, the output voltage X increases. Okay, that's quite large. Let me add another text box. Can I like highlight the text here? Yes, I can. Control X, and then I'll do this. Can I make it smaller? No, I can't. Okay, so this is what we have so far. When a light source illuminates the sensor, the resistance R1 decreases. Then we add context. We say that they form a voltage divider. And using the equation of the voltage divider, we can actually see that as R1 decreases, X increases. Okay? So now what happens next? So when this happens, when the voltage of X increases, do y'all know that the current increases as well? Did you? Okay. Basically it does lah. Alright. So when voltage of X increases, the current here will increase as well. But note that that also goes into the you can't see that that's a B. Note that the current at the base of the transistor also increases. Okay, and we can actually find a relation of that to the collector and emitter pins. Okay, so I don't know. This is more facts. More facts. Okay, this is gonna relate to. Okay, this is gonna be the current at IC, and then the currents, let's say at oh wait, no, not IC, IB, sorry, and the current at IC. Okay, so basically, right, when your IB increases, your IC actually increases. Okay, I'm not sure if they are directly proportional. Let's say they are not, but this graph just illustrates that when IB increases, IC increases as well. How is this useful to us in any way? Remember what the question asks? Explain how the circuit switches the motor on. When IC is higher, the current in the motor actually increases as well. Remember, all the current in a series circuit is the same. So when the current at the motor increases, doesn't that drive the motor more powerfully? Or in this case, doesn't that turn the motor on? So, wait a minute. Did we just make a connection that answers the question? Did we do something useful? Yeah, we did. And that actually answers the question already. So let me write down what I just said, because I just said a lot. Backtracking, right? I said that uh, when the output voltage, okay, voltage X increases, the current at X increases as well. This would also increase the current at the base of the transistor. Then I also said when when the current of when the base current of the transistor increases, the current at the collector increases as well. Okay, then I also said, since in a series circuit all current is the same, the current in the motor increases as the current at the collector of the transistor increases. Okay, therefore, as the light source illuminates illuminates the sensor, the current in the motor increases, as such turning it on. And that's it. Okay, so this is the answer. Yeah, so you can go ahead and try to understand this a bit more. Basically, right, I was just writing facts, it became the answer. But note, right, how I have 4 passages, and actually, right, each passage equates to 1 point. So we got 4 points here. The first point is this, second point, third, and fourth. So what did I just do? Okay, this doesn't just like come out of my head easily. Surprisingly, there is a process to be able to come up with this. So first, what did I do? First, I analyzed what the hell was going on. In this case, it's a circuit, so I analyzed the circuit. Next, I stated facts. Look at all this. I stated how this is the LDR graph, right? Resistance against brightness. I stated that in a voltage divider circuit, right, as the top resistor decreases in resistance, the X actually increases in voltage. I also stated that as the base current increases, the collector current increases for a transistor. I stated facts relating to the circuit. And what else did I did? I actually formed relationships between each sub-circuit. For example, I said that when R1 decreases, the output X increases. So I'm relating R1 to the voltage divider output. I also related the voltage, or the voltage increasing, basically the current increasing, to the BJT. So basically now I'm connecting these two things, connecting them up. And then I also connected the BJT to the motor. So I also made connections. So you may be asking to us, you may be thinking, right, okay, how do I know what connections to form if I don't know what I want? So you need to know what you want. Okay, what you want is for the motor to turn on. How does the motor turn on? The current increases. The current in the motor increases. Okay, how can the current in the motor increase? Here the current needs to increase. How can the current here increase? The voltage needs to increase. How can the voltage increase? The resistance here needs to decrease. How can the resistance decrease? The surrounding lights needs to increase. So, to know what you want, you can work backwards. So that's a strategy as well. By working backwards, you can find out what you want. Okay, so that in a nutshell is what you can do. Analyze the circuit, state the facts relating to the circuit, know what you want. So it's pretty much like 3 steps. And with that, right, that is pretty much what you will need. So let's move on to the next circuit. So here we have a fridge alarm that once the door has been left open okay. So they give us this, and then they say, okay, explain why this type of buzzer could damage a transistor. Explain how this resistor and capacitor create time delay. How switch 1 resets the timing. Okay, so everything you learned here cannot really be applied here, because this is like a different question type. Okay, so yeah, now this is not bad. I'm just going through different types of explain questions. So you can pause the video to try and do these two, like now. Alright, so explain why this type of buzzer could damage the transistor. Okay, this question is not really a lot of thinking. You just need to know some facts. So, okay, I stated this in my, I think my transducers video. You can check it out now if you want. But basically, in this type of buzzer, um, it has a coil inside, and this is basically an inductor. The facts is that when you drive an inductor with a certain current, and then you stop driving it. Okay, wait, sorry, wait. Let me rephrase. When you drive an inductor, okay, believe it or not, this coil produces a magnetic field. Whoa, yeah, that's true. And the magnetic field is sustained as long as you keep driving the inductor. The thing is though, once you stop providing current, the magnetic field immediately collapses. Okay, and it will collapse and turn all its energy right into current. So just now we were supplying it like this, right? The current will now actually flow in the opposite way, and the current can actually spike to amps, as in like it can spike to like 3 amps sometimes. If you're dealing with very big inductors, then thousands of amps maybe. You may be wondering, oh, okay, that's not really a lot, but like 1 amp can damage transistors already. Okay. Anyway, so basically that's the facts. All right. And this inductor is present in the buzzer. So once you know the facts, you can apply it here. Explain why this type of buzzer could damage the transistor. So we know that once we start driving the buzzer, the magnetic field is produced. Once we stop driving the transistor, um, the current will spike, or there'll be a large negative current spike, or large negative voltage spike. That works too. Either way, this large negative voltage spike, right, will enter, or rather it will pull from the transistor at such a rate that the transistor could potentially damage, because transistors such as this transistor here are rated for low current, low voltage applications. So you know how in the previous like question I wrote it all out, right? This one is not hard. It was just facts, so I'm not gonna write anything out. But it's just for you to know. Alright, next part. Explain how the resistor and capacitor create the time delay and how this switch resets the timing. Okay, so this one requires a little bit more thinking. So let's do the steps that I did up here. So first of all, circuit analysis. So there is, let's follow current. The current goes this way, and we notice, right, we can actually annotate a sub-circuit here. This is an RC circuit. And the fact is that an RC circuit can create a time delay. Okay. And we also see that this switch is connected to this RC circuit in such a way that when this switch is closed, note how this capacitor is actually short-circuited to itself. Okay, the fact is, right, let's say I have this capacitor. Let's say it has like 230 coulombs of charge, or 200 volts of charge, or whatever lah. That's a high amount. When you connect it to yourself, it's going to start dissipating that voltage, or dissipating that energy. And if you leave it for a while, right, the charge in the stored charge, right, will be 0 volts. So basically, if a capacitor connects to itself, it will discharge. And this switch, when closed, achieves that, because we can see it short circuits the capacitor to itself. What else do we see? We can see that this RC circuit, right, is interrupted in the middle, not only by the switch but by this transistor. Okay, and we can also see that this transistor is connected to this buzzer. So this here is a transducer driver's transistor circuit that drives the buzzer, okay, or that turns on and off the buzzer. I mean, that's pretty much it. It's quite a simple circuit. So what's the question again? Okay, how does it create a time delay? How does this resistor and capacitor create a time delay? Okay, the facts. Okay, wait. I erased some of the facts. So what was the first thing I said? An RC circuit creates a time delay. Okay, but I'll go into that with more detail. Basically a capacitor connected to itself will discharge itself to 0 volts. That's what I said. Okay, a capacitor takes time to charge up. So if I were to look at a voltage to time graph of a capacitor, if I apply a voltage to the capacitor, it does not immediately jump to that voltage. It will actually, control Y, it will actually take some time to get to that voltage. Okay, that's the facts you need to know. And if you add a resistor, if you increase the resistance of that resistor, it actually takes a longer time to reach that same applied voltage, or to charge up. It takes a longer time to charge up, basically. Okay, so yeah, that's the facts. Okay, so I think that's pretty much it. That explains how it creates a time delay. So basically, the very fact that it takes some amount of time to charge up to the applied voltage, that amount of time can be used as a time delay. So let me put it into words. So a capacitor takes a certain amount of time to charge up to the applied voltage. When a resistor is used and the resistance is increased, the time taken to charge the capacitor increases. Okay, that's the fact that we just said. So this amount of time to charge the capacitor can be used, to create a time delay. I think that's pretty much it. So yeah, that is the first point. Alright, and how the switch resets the timing. Okay, so when we already stated the facts, or I already said in the circuit analysis, right? When the switch is closed, the capacitor will be shorted to itself, or I suppose you can say connected to itself. Okay. When this happens, the capacitor will start discharging, and this will effectively, this will basically reset the timing the timing. Okay, we don't have to go into further depth, cause like that's pretty much. Okay, that's pretty much it. It is 2 marks, so these 2 points should be enough. So that's pretty much it. Alright, this is the last question I'm going to go through, and I think this one takes. Okay, no, this one's not beefy. I suppose it's okay. So you can pause here to try read it. Okay, no, I'll read it. So, okay, you can't really read because Jovia can't take a good picture. But basically, there's this game show, right? And then there are 2 buttons, okay? And one is for player A, one is for player B. Basically, the first player, and it's a quiz, it's a quiz game. So, you know how like in the TV or whatever, the person who can come, when the host asks a question, the person who is quicker will press the button to answer. Okay, so basically, this circuit makes it such that when one person presses the button to answer, you cannot answer if you don't press the button. Once, let's say player A presses the button, player B can press the button, but that signal will no longer be observed. Vice versa. Okay? Oh, wait. Basically, when player A presses their button, their LED will light up. And then they'll make it such that player B's LED will not light up, vice versa. Okay. Then now they're asking, how does the logic circuit here actually prevent the other player's LED from lighting up? So let's do some circuit analysis here. Okay, we got their buttons, the player's buttons. These are just some pull down resistor for logic. You know that the works. I probably have a video on this, so you can go check it out if you don't know what's going on. Okay, next, their inputs are actually connected to this thing here. So what this is actually an SR latch. I know that you are taught, or I have taught, that an SR latch is with NOR gates like this. But I'm pleased to inform you that you can actually create an SR latch with NAND gates as well. It works the same way. Okay, let's move on. Next, we have these NOT gates, which will invert the output of this SR latch. And then we have LEDs, which will, I suppose, show the which person like answered lah. So, I forgot to mention, but they can't just press once. They have to press and hold to not allow the other player to light up their LED. And it says somewhere here, yeah, presses and holds down their switch. So, okay, we gotta figure out how it works now. So let's state some facts. Okay, in an SR latch, okay, how do you determine which pin is the set pin and which pin is the reset pin? Okay, how do you determine? So I think I have told you to memorize it such as, like, if you say this is R, then this is Q. If you say this is S, then this is Q bar. So yeah, this is the facts. But what else you should know is that when R is 1, this is 0. Or when one pin here is 1, the opposite side pin is 0. When this is 0, this is 1. Okay? When set is 0, this will be 1. And when set is 1, this will be 0. I can prove this. Let's use a truth table. Let's use a truth table. So in a SLS truth table, we have S, R, Q. Let's have Q bar, okay? So an SR latch saves data, right? When both S and R are 0, Q and Q bar will be what is saved. So we don't know what's here. So let's just like shade it out because it doesn't matter. When set 0 and you reset, when you reset the entire SR latch, Q will be 0. And since Q bar is opposite of 0, it will just be 1. When you set the state, right, it basically sets the inside to be 1. So Q is 1, Q bar is 0. And when both are 1, you're setting and resetting at the same time. The SR latch goes what? And it explodes. So we don't care about this either. I go in more depth in this in an SR latch video. Okay, yeah, the video is a combination of other like circuits, but it gets the job done. Alright. So how does this help, or how does this prove what I said just now? What I said just now is when R is 1, or when this side is 1, the opposite side will be 0. Let's see. When R is 1, here, Q is 0. It's true. When S is 1, Q bar is 0. It's true. Oh, it's true. Oh my gosh, it's true. I'm right. So this is the proof that when one side input is something, the other side output will be the inverse of that something. Okay? And that is a fact that you need to know. Why? We'll see. That's just a SLH fact lah. So we're just writing down facts on the we're just writing down facts about the circuit here. Then next we have a NOT gate. You can write down the fact that a NOT gate inverts its input to the output, right? But I won't, cause that's basic knowledge. And then that's pretty much circuit analysis done. So okay, this is 3 marks, so we need 3 points. How do we even start? What do we want? We want when, let's say when A is pressed, we want it such that LED A will turn on and then this cannot at all. So how do we get that? We need to make it such that LED B will be 0 here and LED 1A will be 1 here. And to get that, there's an inverter here, right? So we need to invert this. And then remember how 1 here will be 0, 0 here will be 1. I think I just explained it. So basically, when this is closed, this will be a logic 1. It will go here. Due to the nature of an SLH, this will be 0. It will invert, this will be 1. But since you press and hold, this will be forced into 1. And as such, this will be 0 LED B. Okay, wait, this is a bit weird because, yeah, this doesn't really work. What if both of them press? Then the output will be invalid. Yeah, this circuit is a bust. Yeah, whoever wrote this circuit, wrote this question, I don't know. Anyway, so, how do we explain this? Can we just say, can we explain by giving an example of, for example, when A presses their button? Or do we have to write it in like a more abstract manner? When A presses their button, the secondly, right, I don't really know what to call this pin, because yes, it's an SR latch, but can you really say that this is S? Because this can just be R and then this is Q. This can just be S and then this is Q bar. Secondly, can we just say due to the nature of an SR latch such that when the input is 1, the opposing output will be 0? You can't just say that either. So this is slightly odd. So we may have to go about stating that this is S and then this is Q bar, this is R and then this is Q. Okay, so when A is pressed, the SLH will be set, and this will force the output of D to be 0, since the output of D is Q bar. As such, the 0 will be inverted to a 1, which will power the LED A. When this would, since the SLH has been set, Q, or the output of C, would be 1. After inversion, it will be 0, and as such, the input of LED B will be 0, so the LED B will be turned off. Okay, so that is not an abstract way, but is there a way to explain this abstractly so I don't want to state that this is A or whatever? The reason why I'm even considering answering it this way is because the question doesn't ask How does the logic system prevent B's LED from lighting up when A presses down? It asks, how does the logic gate system prevent the second LED from lighting up? When a contestant presses and holds their switch, it will cause the state of the SLH to be changed. Okay, you know what? I'm just gonna explain this not in an abstract way, because I mean, if one meaning like if one is already pressed, the other one doesn't light up. Yeah, I know. Yeah, I'm just gonna explain this in the not abstract way because it's, I'm not even getting paid for this. So anyway, so um, how do I even start? For example, when A is pressed down, explain how the logic system prevents the second LED from lighting up. Yeah, if you're really stuck, you just repeat the question to yourself like 50,000 times and eventually you'll get it. Okay, how I'm gonna go about it is I'm just gonna say when A is pressed down, blah 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 blah. This can also be said for B. Yeah, okay, let's just do that. So when A is pressed down, okay, then we need to say okay, wait, before this, let's add some context. Let's make it such that we state the pin names of this SLH. Okay, C and D are configured in an SLH. Okay, let it be known that the output of C is Q and the output of D is Q bar. Let it be known that the input of C connected to button B is R and the input of D connected to button A is S or set. So wait, let me, instead of saying R, let me say reset lah. This is set. Okay, then let it be known that the output of C, instead of Q, let's say, let it be known that the output of D is the inverse of the output of C. Then let's remove this entire part. So what I've done is I've stated facts. Can you actually do this in the exam? Yeah, this is fine. So we're just stating facts. C and D are configured in such a way that it's an SLH. Let it be known that the output of D is the inverse of the output of C. Let it be known that the input of C connected to B is reset, be set. So we're just stating the terms of our SLH. Then now we're going to start explaining how it is stopped. How it goes. So this is our first. This is maybe they will award marks for this. I'm not sure. They might just like screw it and then not. Yeah. So when A is pressed, the input, the set of the SLH is logic 1. Okay, then what happens then? As such, the output of this would make the output of the output of C logic 1 and the output of D logic 0. This okay, it is 3 marks, so I'm not gonna I'm gonna spend a lot of time explaining why this happens, so I'm just gonna say this is due to the nature of SI latches. Yeah, okay, I'm gonna fail this question. Okay. Next. Okay, wait. Everything is okay. Let me shift this down. So the output of D passes through a NOT gate. Oh, okay. Let's add in the context, right? Let it be known that a NOT gate inverts its input at its output. So yeah, we're just adding context. We're just buying insurance. They're not gonna mark you down for this, obviously. They're chill. So partial through the output of D passes through a NOT gate, becoming logic 0, becoming logic 1. This powers the LED A. The output of C passes through a NOT gate, becoming logic 0. This forces the LED B to be turned off. Okay, and that's pretty much it. We can add a concluding paragraph. As such, when A is pressed and held, the output of LED A will be turned on and LED B will be forced to be turned off. This can be said the same when B is held, where LED B will be on while LED A will be forced to be turned off. Yeah, okay, you will get the mark here, but the wording is kind of weird. Because, I mean, this is a goofy question. Okay, so that's answering techniques. I've held you around for about an hour, I think. I have lost all concept of time. So I hope this helps. Thank you for watching. Thank you for, yeah. So to summarize, analyze what's going on. If it's a circuit, analyze the circuit. If it's a circuit, you can actually circle some sub-circuits, like for example a voltage divider, an RC circuit. Then state some facts relating to the circuit. Then figure out what you want. To figure out what you want, either be very smart or you can try to work backwards to see how you can get what you want. So that's pretty much a 3-step plan. Thanks for watching.